Hey everyone, we're going to continue our discussion about kinematics and in particular with velocity to talk about something called relative velocity. Now, the question is, how do we determine our velocity? How do we tell if an object has a certain velocity? And the answer is, well, it depends on how we frame our reference. And that's actually the important thing is this idea of reference frame. For example, if you go onto a treadmill and you start running on the treadmill, well, depending on how you dictate what you're comparing your motion to, will change what your velocity is. Are you comparing your speed relative to the map, like the track? Well, then you would have one speed. But if you are comparing yourself to the ground, well, then you'd have zero velocity because you aren't actually moving anywhere when you're on the treadmill. Now, there are a lot of ways that you can dictate the velocity. So, for example, a lot of times you would be dictating how fast something is traveling relative to the Earth. That's the most common example. Now, if I'm sitting at the front room, in my chair, you would normally say that I am motionless. However, if you were looking outside of the Earth and you were taking into account that the fact that the Earth was rotating and you saw me rotating on the Earth, you would actually say that I had a speed of 465 meters per second, or a little bit under 1,000 miles an hour. If we went outside of the solar system and we saw that the fact that the Earth is actually also moving around the sun, then we'd end up having a speed like 30,000 meters per second. If we take it a step further and take into account that the solar system is moving around in the Milky Way, then my speed becomes even bigger. And I can keep doing this. So, depending on what I am actually dictating as my reference frame, how I'm looking at the scenario will change how I perceive my motion. Now, let's consider the case where I'm driving on a highway and I'm traveling at 35 meters per second, which is about 65 to 70 miles an hour. And let's say the person decides to go past me because I'm going too slow and they try to bypass me. Can I figure out how fast he's going? The answer is yes, I actually can. Uh, Based off the fact that I know how fast I'm going, if I know how fast he's going relative to me, that will actually allow me to find what his speed is. Now, there's actually a bunch of videos that I have up here. These are all really good at showing this idea of different reference frames and showing different perspectives. I actually really like the drone cam, and the car and the treadmill is fine for different aspect, but the drone cam is really good at showing how objects' motion will change depending on how you're perceiving them, whether you're viewing it over one car versus another or over the ground. So I do recommend that you follow these links and you check them out. Now, there are two different types of relative velocity questions. One example is that you have two moving objects and you're trying to see how one object is moving relative to another. Typically, one way that they do this is that they represent the two velocities using the terms, with subscripts, as in like VA and VB would represent the velocities of the two different cars, or in this case, it's a person and a car. So VA could be a person, VB would be the car, and then VAB would represent the relative speed. In this case, the speed of A relative to B. This would technically be different than if we represented the speed of B relative to A. Basically, it would just kind of flip the direction. Now, if you want to figure this out, you would use this equation. VAB is equal to VA minus VB. Now, one thing to note is that these are velocities. So if one object is moving to the right and the other object is moving to the left, you do have to notate that with a negative sign. So this is assuming that they're all moving in the same direction, or VA and VB are moving in the same direction. These are actually some animations that I want to show that really, I think, strike home as to the idea of how changing your reference frame changes how the object moves. So in this scenario, we have a situation where the map is stationary. So we have the edges of the map stationary. And on the river, there are these logs that are traveling down. And we have a boat that's traveling back and forth across, and it's missing all these logs. However, if instead of focusing on the terrain, I instead follow the path of the stream or the logs so that they look like they're motionless, everything else would instead move, and we would again see this boat constantly missing everything as it bounces back and forth. This is another example where we have the map frame where the object is where everything is stationary, and then we can see the object fling off and go towards this opening. While over here, we are actually traveling and spinning with the object, and we can see that the object will still end up going through that little hole. So these are a variety of different ways that you can kind of imagine. It can get a little tricky trying to envision these types of things. The good thing is that relative velocity questions are not super common. This one's another one that I do kind of recommend, and it kind of shows that as if you change the velocities of objects but keep their relative velocity the same, you'll notice that the motions always end up being the same thing. They'll end up colliding at the exact same time. This one's really cool to play around, and I highly recommend that. This is the other type of relative velocity question, and this one's a little bit more common, especially in the regions class. Uh, Typically, what this question is referring to is essentially when you're moving on a surface that is also moving. So in this case, in the images here, we have a plane traveling and the wind is going to move in different directions. The first one, the wind is moving in the same direction. It's a tailwind, so it's pushing them in the direction that they're moving. Then we have the headwind, which is pushing in the opposite direction. And then the last animation is what would happen if a wind was blowing from the right, so it's a crosswind, and you would see that the object ends up moving on this diagonal. Even though the object is pointed in a certain direction and basically thinks that it's moving in that straight direction, you'll find that it's moving crossway. This one's really interesting. The way you'd end up doing this is using the vector addition. That I mean, it's kind of what we do for all this, but you're always doing vector addition. So with the crosswind, you would do like a little right triangle, do Pythagorean theorem to find the resultant. Nothing crazy. But this one's actually really interesting because there are a lot of animations that you might find online. I did not find them in this scenario, but you can find them of planes having to land with really strong crosswinds, and you'll find that they end up having to actually change the angle of the plane so that they can move in a straight line. As you see here, if the wind is moving to the coming in from the east or something and moving the plane on this diagonal, the plane will never be able to land on a straight um, uh, airway. So in order to actually land the plane in a straight way, they will actually have to take into account vectors and cancel out the wind vector and point in the other direction so that they move in a straight line. And it ends up looking really weird from the perspective of the people on the ground. So I do recommend that you try to look that up as well. If you want, you can ask me in class and I'll show you the animation. Uh, that's it with the relative velocity. Like I said, there are two very basic questions, but we'll see how these questions kind of come up in some of the problems. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.